Hello, in this video we're going to be talking about derivatives of unique functions, particularly logarithmic and exponential functions, which have very weird graphs and therefore very weird derivatives. So I'm just going to tell you the answer to this. The derivative of e to the x ends up being just e to the x. And you might be wondering, well, why is that happening? Well, I'll show you real quick here. So I pulled this up. I've got my tangent line here, and I've got the graph of e to the x. You can see here at this point, the slope of this function is basically zero when we're down here. So when e to the x is basically zero, its slope is also basically zero. As our tangent line shifts over towards this side, and as e to the x starts getting very large and large, you can see that the slope of that tangent line also becomes very large. And then at 1, this is the really exciting one that you can see, is right here that at this value of 0, the slope ends up being 0 when the e to the x equals 0. Look, it's perfect. 1 up, 1 over 1 all the way across. So the derivative of e to the x ends up being just e to the x. The only thing that we have to worry about is if there happens to be stuff inside of our e to the x function. We do the derivative of whatever that exponent is, and then then just e to the u. So in this case, our u, the thing on the inside there is that 2x. And then we find, what is the derivative of that thing? Well, it's just 2. So y prime, or dy over dx in this case, means the same thing, is u prime, which is 2, and then e to whatever u is, in this case, 2x. And that's our derivative. Let's do that one more time for funsies. So our u, again, is just x squared. So then our du, or our u prime, is going to be the derivative of that, which is just 2x. So dy over dx is just that u prime, in this case, 2x, and then e to the x doesn't really do anything. In this case, e to the x squared. And that is our derivative. Now, this e to the x thing does not happen all the time that you see an e. So in this example, when we're trying to find what our derivative is, this is just a power rule. Sure, there's an e in it, but it's not an e to the x. X is the base of this thing. It is not an exponential. It's just a weird kind of polynomial thing. No, it's not even a polynomial. It's just a power rule problem. We're going to drop our exponent, 1 minus e, and then we end up with x to the 1 minus e, and then doing our power rule says, hey, subtract 1 from that exponent. Think about 1 minus e is a number just like anything else. So I'm going to put parentheses around that to be proper. So we get 1 minus e multiplied by x to the, well, 1 minus 1 in that exponent is going to be 0. So we're left with just a negative e. If we wanted to clean it up a little bit more, we could write 1 minus e over x to the e, but you can see how that changed radically from what we had originally. It's not following these properties up here because it's not using those properties up here. This is just a power rule problem. Now, we could go through and show other reasons why this 2 to the x is this monster up here, but we've got better things to do. So we're just going to take this derivative at face value. If I wanted to find f prime of 0, so okay, then I'm going to do the thingy up there. So I need to start with just a to the u, which is 2 to the x. But we're doing f prime of 0, so we're just going to put in a 0 everywhere there is an x. And then it's got an ln of whatever our base is. In this case, our base, that a, is 2. And then we need to do the derivative of whatever this exponent is. So what that exponent is, in this case, is a 1. So f prime of 0 is 2 to the 0, which is 1, times the ln of 2, which is a thing, times another 1. Well, that's just an ln of 2. So the slope of our tangent line at 0 for this function is the ln of 2. We can see that same thing if we actually use our limit notation in order to figure out that same value. I am going to use the top one because I don't want to deal with this C plus H, and they kind of work out to be the same, but this is just going to kind of make me sad, so I'm just going to use that top one. So then f prime of 0 equals the limit as x is approaching. The value that we're trying to get to is c, so that's kind of why I don't want to use that bottom one. It's the same kind of thing. F of x, so in this case 2 to the x, minus f of c, which is a 2 to the 0, over x minus our c value, which is 0. And you can also see that that x minus 0, that's just an x, which is, again, similar to that bottom one, over 2 to the x minus, and 2 to the 0 is going to be just a 1. So this is the limit as x approaches 0 of all that. That is equal to f prime of 0. Now, the cool thing about this derivative stuff is I can't figure that out. I don't know. I don't have ways of dealing with that limit. I can't do it. I can try to direct substitute, and it just doesn't quite work out. However, because we know what the derivative is at that point, that derivative is going to be equal to this limit. So using the idea we got in the last problem, we can say, hey, guess what? This limit is going to be the ln of 2, because that's the value of the derivative at that point, based on the assumption we made in the last part. Taking this idea a step further, we can see this one and we can say, hey, that looks a lot like what we just got. It's got a 7 to the something minus a 1. That could have been 7 to the h minus a 7 to the 0 over that h. So this must be basic, then equals limit, forgot limit. This is basically asking what is the value of the derivative of something. So we could say let's call it g prime of 0 for g of x, that is x 7 to the x. I got there, I wrote it, but I wasn't saying it right. So this is basically asking about what is the value of the derivative at 0, because it's a limit notation of our derivative, and it seems to, the function it seems to be using is 7 to the x. Well, I can't figure out that limit. I can figure out the derivative of this thing at that point. So I can find g prime of 0 using this information up top. We can do a to the 0, or a to the u, which is 7 to the 0. Then an ln of a, our base, 7, times the derivative of our exponent, which in this case was just an x, which is 1. So 7 to the 0 is 1. So this is the ln of 7. So we can say that the limit as h approaches 0 of 7 to the h minus 1 over h equals the ln of 7. Ha ha! Moving on to a different type of derivative, natural log has this odd thing. Again, we're not going to prove it, but natural log ends up being 1 over whatever is inside of the natural log multiplied by the derivative of what was inside of that natural log. You might even see it as like u prime over u. That's another way to write it. It's just up to you how you want to do that. So if we wanted to figure out what f prime of x is, finding our derivative, we say, okay, f prime of x is going to be 1 over what was on the inside, 2x plus 2, multiplied by the derivative of that inside. So the derivative of this piece right in there. So the derivative of 2x is 2, and the derivative of 2 is 0. So this ends up being 2 over 2x plus 2. We could simplify it if we were feeling fancy, but we're not really in the simplification game. So this would be the derivative of our function. To determine our domain, we go back to our original function. We say, well, for logarithms, that 2x plus 2 has to be greater than 0, because we can't put in negatives or 0 into logarithms. So that means x has to be greater than negative 1. If we check down here, this is just saying, hey, x, we definitely don't want -1 because we're not going to be differentiable at that point, because we wouldn't be able to put in that -1. So based on the original function, it says, hey, you got to be greater than 1. The derivative says, hey, you don't want -1, but we still need to look at our original function. So we want to make sure, hey, we're fine. If this had been x needs to be greater than -2, then we would have need to say, oh, but also don't do -1 because it's not going to be differentiable there. Last problem we're going to look at, we've done an e to the x, we've done a number to an x, we've done a natural log. So what about logs with other bases? That requires this function right here. It requires a natural log. So we just need to figure out what's going on with our derivative here. Just plug and chug. Our u is going to be x plus 1. Our u prime is going to be 1. So this derivative, f prime of x, is going to be 1 over our u, which in this case is x plus 1, multiplied by the ln of a, which is the base of our logarithm, multiplied by u prime, so the derivative of that thing. Oh, wait, sorry. Square root of x plus 1. So that is going to be, instead, drop our exponent, up, 1/2 x plus 1 to the -1/2. Future u, double check that we've done the chain rule properly. We have, but future you currently don't know how to do the chain rule, but future you should. Multiply by this thing, so times 1/2 x plus 1 to the -1/2. If we wanted to do some work to clean this up, then we'd only have a 1 in the numerator. This x plus 1 to the -1/2 would go to our denominator and get tacked on with this other x plus 1. So we get x plus 1 to the 3/2 and an ln of 10. That is our f prime of x. Our domain would say, hey, we got to make sure that we stay greater than or equal to -1, and our domain here would agree with that. So ends this video about unique trig functions. I'm going to throw in sine and cosine there just as a quick reminder of how sine and cosine also don't want to follow the rules. But e to the u is just an e to the u, and an ln is 1 over u. These come up from time to time. They're not as common. These are very common. These are very common, so we need to make sure that we know those derivatives, and we just got them memorized so that we have them handy when we need them. Thank you so much for watching. Bye-bye!